Now to our next session here on the stage. I am 100% stoked that it's going to be about artificial intelligence. Because you know, all of the bestest, most awesome products that I use and love that have come out the recent years, they all use artificial intelligence in some way. For instance, SwiftKey, the iPhone app, that kind of like changes how the buttons are on my phone so I can type better. Google and Apple have made it possible to search for cat in my photos so I can get all my cat photos straight away. My robot vacuum cleaner is like, so good. But so now during this session, we're going to meet 5 more exceptional women. And yeah, I think it's time to go beyond conventional human intelligence. And let's get started with AI. Our first speaker is here to tell us that not everything is fun and games in the world of AI, because running neural networks can be really, really energy consuming. And that's bad if we want our planet to be alive. But she is one of the people, I think, who will try to solve that problem with her research. She is, get this, part of the Neuromorphic InMemory Computing group at IBM Research in Zurich. Neuromorphic. Sounds awesome. She aims to give us the next generation of AI systems and that are also energy efficient. Please welcome to the stage, Irem Boybat!
So hello everyone. It is actually pretty amazing to be on stage today with such a great audience. My name is Irem Boybat, and I'm a researcher from IBM Research Zurich. And today, I want to share with you IBM's efforts on developing the next generation of AI systems. So we aim at developing systems that have unprecedented speed and significant energy efficiency to fully exploit AI's capabilities. We live in the big data era. And to understand how much data we generate, let us consider these statistics. We generate 2.5 exabytes of data every single day. And it is not only the amount of data we generate, but also the pace that we generate this data. 90% of the data we have in the world today has been generated in the last 2 years alone. And also what is very interesting for us working in the research field is that the global scientific output doubles every 9 years. The accumulation of this ever-growing data has led to the third era in computing, the cognitive era. First, we transitioned from the mechanical systems of the tabular systems era into the electronic systems of the programmable systems era, with huge improvements in storage and performance capabilities. Now, we have entered the cognitive systems era, where systems can now make sense of data by learning and by reasoning with us and with feedback from us humans without needing explicit programming. So the question is, what can now AI systems of today in this cognitive era do? Utilizing the vast amount of data that we produce, we created systems that show similar or even better performance than us humans in various cognitive tasks. For example, in image classification, in strategic games, in speech recognition. And moreover, we have managed to combine these skills to create even more advanced systems. For instance, last year, IBM launched the project Debater. This is the first AI system that can debate with humans on complex topics. To be able to do this, Project Debater is equipped with various skills, ranging from natural language processing to argument construction, from content organization to emphasizing words and phrases in her speech when she replies. It is indeed very impressive. Among the broad class of AI algorithms, deep learning has proven to be significantly powerful. We have been seeing products of deep learning even in our everyday lives. Deep neural networks are used heavily in developing the project Debater as well. Using this vast amount of data, we have managed to increase the capabilities of deep learning systems. In the recent years, these networks are getting bigger and bigger in size, and deeper, and managed to exceed the human error level in various tasks. And such systems are continuing to evolve. Their capabilities are continuing to grow, thanks to advances in algorithms and also the presence of big data. But here, the question we should ask ourselves is, this is happening at what expense? Training a single deep neural network model requires significant amount of time, which can be quantified in days, or sometimes even weeks. It is estimated that training a single deep neural network model is equivalent to 3 weeks' energy consumption of a single person. It is also estimated that training a single neural network model is equivalent to 2 weeks of carbon emission of a single person. What this says to us is AI is costly. And why is that the case? Why is AI so expensive in terms of resources? And the answer lies in how we do computing today. Today's computing systems are based on von Neumann architecture, where memory and processing are 2 separate entities. To process data, we constantly move the data between these 2 units. And this makes such systems very inefficient, especially for data-intensive AI applications. Instead, what if we had an architecture where we could do some of computing tasks, avoiding data movements in the memory itself? And this is what we call in-memory computing. Such a computing architecture is actually very familiar to us because our brains operate with a similar principles. In our brain also, memory and computation are collocated. So these systems are loosely inspired by the working principles of our brains. Now, we are also investigating about how we can build such systems in a more efficient way with the help of new technologies. In particular, we focus on a new class of devices, and the non-volatility and the nanoscale dimension of these devices is estimated or is envisioned to translate to significant energy and density gains. Using tailored arrays of such devices, we target at solving some of the operations that are highly relevant to AI workloads in an analog manner. As IBM Research, we believe that performing computing using analog cores shows great promise for the future of AI systems. We estimate, or we foresee, that computing with such analog AI cores will give us 1,000 times efficient systems in the next decade. We are not trying to replace today's computing systems, but we are trying to rather enhance them, to improve their capabilities using general-purpose AI cores, dedicated analog deep learning coprocessors, and more biologically plausible neuromorphic coprocessors, and this may make up the future of AI systems. So thank you.